Hello friends, this is a short video on various transform and their interrelationship used in signal processing. The first one is a Fourier series, which is applicable to only periodic function and it gives a spectrum of a signal. The limitation of Fourier series, which is applicable to only periodic signal, is overcome by Fourier transform, where Fourier transform is a dot product of x of t with e raised to minus j omega t dt. However, the Fourier transform doesn't give transient behavior of the signal and system, and this limitation of Fourier transform is overcome by adding a model which shows the transient effect whenever signal is transmitted through any system or a channel, and it is modeled as exponentially decaying function e raised to minus sigma t, and hence the effective model of the signal becomes x of t into e raised to minus sigma t. Whenever it is substituted in Fourier transform, the equation gets simplified with a new variable s is equal to sigma plus j omega. Here the sigma is called attenuation constant and it is arrived because of the transient model e raised to minus sigma t introduced in Fourier transform relation. Now omega here is a frequency which is equal to 2 pi f. Now all the three transform, that is Laplace transform, Fourier transform and Fourier series, are applicable to the analysis of analog signals and system. How can one apply Laplace transform to discrete time system? So here the initial process is sampling of a signal at regular time interval Ts using train of impulses. The sampling signal xst is an analog signal x of t multiplied with train of impulses s of t and which generates x of nts. So here the parameter t becomes nts, and whenever it is substituted in a Laplace transform formula, that is st is equal to sigma plus j 2 pi f into nts. Now ts is sampling period which is equal to sampling frequency as 1 by fs. Whenever it is substituted in equation st, then the new equation form is n equal to sigma ts plus j 2 pi f into n. And now you can substitute this equation in e raised to st, which will give the two terms e raised to sigma ts raised to n into e raised to j 2 pi fn. Now here n will become a power and the new equations found are r is equal to e raised to sigma ts, a real value, w is equal to 2 pi f, where f is equal to f by fs, which is called normalized frequency or a digital frequency, and therefore the substitution of these two terms will become e raised to st is equal to r into e raised to j omega raised to n. Now here r is a real number, e raised to j omega represent a complex number, and hence it represents a circle and also a complex number which is r cos omega plus j into r sin omega, and hence it is denoted as a variable z. And therefore e raised to st becomes z raised to n, where z is equal to r into e raised to j omega. So after discretization, integration will become summation, and hence the new transform, which is a function of z, it's called z transform, and that is given by x of z is equal to summation n is varying from minus infinity to plus infinity into x of n z raised to minus n, where z is equal to r into e raised to j omega. Now sampling can be applied to the Fourier transform relation as well in time domain, where t become nts. So in this equation, if you substitute sampling where t is equal to nts and integration becomes summation, you'll get a new transform which is called discrete time Fourier transform. So it is a discrete time counterpart of analog Fourier transform, and after substituting directly, you'll get a relationship x of omega equal to integration becomes summation, where summation varies from n equal to minus infinity to plus infinity x of n into e raised to minus j omega n, where omega is a digital frequency and that is equal to 2 pi f, which is we already computed. In z transform, if you substitute r equal to 1, that is evaluating z transform on the unit circle, then z transform becomes x of omega equal to summation n is varying from minus infinity to plus infinity x of n into e raised to minus j omega n. This formula is derived from x of z. So here this equation is same as discrete time Fourier transform, and hence z transform on the unit circle is nothing but the Fourier transform, that is a discrete time Fourier transform. Now when discrete time Fourier transform is sampled in frequency domain over 0 to 2 pi at interval d omega, which is equal to 2 pi by n, which is quite obvious from this graph, then d omega equal to 2 pi by n is equal to 2 pi df. Therefore, the kth frequency value, that is a wk, is equal to k into dw, which is equal to 2 pi k by n, and it is also given as 2 pi fk. When these two equations are equated, you will get the kth frequency value is equal to k by n, and that is equal to fk by fs, and hence fk is equal to k by n into fs. So one can derive the value of analog frequency from kth frequency being k, given the number of samples n. So this formula gives discrete Fourier transform, and when it is solved using a fast algorithm in decimation in time or decimation in frequency, it gives fast Fourier transform as shown here. So one has to understand, so when Laplace transform is evaluated with attenuation constant 0, that is on the j omega axis, it becomes Fourier transform. There is no big difference between Laplace transform and Z transform. Both are same. Only Laplace transform is applied to the analog signals and system, while Z transform is applied to the digital or discrete time signals and system. When Z transform is evaluated on the unit circle, which is nothing but Laplace transform evaluated on the j omega axis, that is a sigma equal to 0. Sigma equal to 0 implies radius is equal to 1. So this is an interrelationship between Laplace and Fourier transform, and hence Z transform becomes discrete time Fourier transform, which can be obtained by sampling Fourier transform. Once discrete time Fourier transform is sampled in frequency domain, it becomes discrete Fourier transform, and fast algorithms of discrete Fourier transform are known as a FFT algorithm. So this is what, in nutshell, the overall relationship between various transform used in signal processing subject. I hope you must have enjoyed this short lecture on various transform, and thank you for your patience and watching my show.